reservations in two-way slabs by means of yield lines. This video deals with the cases 11 to 15, which is the case where a concrete slab is on two adjacent sides fixed and the other two sides simply supported. And we will handle here case 15. Case 15 is about a reservation in a slab attracting the yield lines. So case 14 was a centric reservation. This one is a reservation, not necessarily centric. So it's just a reservation in the slab, but instead of using 30, 45, 60 rule, we use the rule of attracting yield lines. So this is a reservation in the slab with dimension D1, D2, but now we have to put the position right, which is D4 and D5. It fixes the position. But what we do is we add D5 and D6, but we have two more equations because now we have the summation of this will be A and the summation of those will be B. So we have two equations more, but we have added for ease of use two parameters. Tracking yield lines is very simple. And now we have the yield line for the negative bending moment, left and top, right and top. Two-way slab, B must be between A and 2A. The maximum hole size, of course, D2 and D1 will be smaller than B and A. And the position, well, you can say, or the sum must be A, or the sum must be B, or you can write it like that too. So I did both. We look now at different possibilities. So you see this is now a reservation in a slab attracting yield lines, and it can move all around in all kinds of shapes around the slab. Again, you see that if this reservation is coming too close to the edge, then this yield line is not very realistic. This will not happen like that. It will go straight. So we must take care of those small values of D1, D2, D3, and D4. Now, we will calculate the work done by the external forces. It's the sum of rectangles and triangles. The triangles are the four corners. And now they have different sizes. So you have, for instance, for this D4 times D3, and for this we have D5 times D6, D6 times D3, and so on. So you have the four corners, 1, 2, 3, 4. Those are the four corners. Mean deflection is delta over 3. And then what's left are the rectangles. So that's easy. It's D2 times D3. It's D6 times D1 and D4 times D1. And no, that's D4 times D1 or D5 times D1. Okay, now we calculate the work done by the internal forces. And it gives us always the same system. I take this yield line, I project this to this axis of rotation, so the length is d4, and the angle of rotation is delta divided by d3. So that's d4 divided by d3. And take this yield line again, project it to this axis of rotation. So now the length is d3, and the angle is delta over d4, which is that. So we can now do that for all the yield lines which are there. D equals E, so M is Q times EX over DX. And the bearing capacity is 100 times M0 divided by M. Again, M0 is defined with the 30, 45, 60 rule, not with the attracting yield lines. This you cannot write it in a simple way, so that's why we do it in steps like this. So this type of case 15 types of holes, they have restrictions. Then we put down the restrictions. You know that alpha 1 is D1 divided by A, alpha 3 is D3 divided by A, and alpha is B over A. That gives you an example how to work with it. We have a concrete slab of 250 millimeter, depth, concrete over 30, floor finish 1 kilonewton per square meter, with a mobile load of 10 kilonewton per square meter. And there is a reservation in it of 1.5 meters, with this as the width, which is 9 minus 5.1 minus 1.5. And this gives you the situation or the location of the reservation. And we draw the yield lines and we use the rule of attracting yield lines. Okay. Now we will try to find the needed reinforcement. The load in ULS is then 1.35. Permanent load plus 1.5. Mobile load gives you 24.79 newton per square meter. These are the different parameters. We use the formulas of the previous slides and obtain as a bending moment 34.51. We will convert that into reinforcement. So we calculate the mean lever arm, which is 212 millimeters. Calculate the needed reinforcement. It's 457 square millimeters per meter. So this is diameter 10 every 110 millimeters. This is too small as a grid. It's quite small. So maybe it's better to use a bigger diameter. So we redo the calculations. We take diameter 10. We recalculate the mean lever arm, which is 210 now. We calculate the needed reinforcement, 462. And you see diameter 10 every 170 will also be fine. We can put it in a graph, alpha 4 on the x-axis and the bearing capacity on the y-axis. You have this situation. Remember that we have a lot of parameters because this reservation can be put anywhere, any place on the slab. So this for 1.5, because this divided by that is 1.5. Alpha 1, which is this dimension, 0.1. Alpha 2 is 0.4, is this dimension. Alpha 3 is this dimension. And alpha 4 this. And alpha 5 this. And alpha 6 this. So, for instance, for this point, we will see that for alpha 4 equals to 0.72, the bearing capacity is 0. And for this particular reservation, we got the maximum bearing loss, which is 10%, almost 10%. So just be clear that the U1 over D2 is always the same reservation, is 0.1 times 0.4 times A. So it's always the same reservation, but we are moving it from left to right, from right to left. And you see this, what's happening. And then the other point is 0.22. So it's something like there. Yeah. So here, the bearing capacity is 100%, 10%, 90%, 100%. So you see that by moving this reservation into the slab, by making a proper choice, you can minimize the influence on the bearing capacity of the slab. So this function calculated with alpha 1.5, alpha 0.1, and alpha 2, 0.4. That's how this formula is calculated. Now, we've seen two different choices of yield lines, the 30, 45, 60-degree rule and attracting yield lines. Which one now will we use? Let's make a very quick comparison. We have a square slab. No, it's not a square slab, almost square. We have a slab of the type, and we have a reservation in it. The reservation location is on the same size, the same conditions. And you see this is using the 60 degrees, 30, 45, 60-degree rule. This is 60. 45, 45, and this is 30. Then you got this pattern. So it's not a square, it's a rectangle. And then we use our attraction by yield lines in this pattern. So now we have the two cases. When we calculate it, we see that the bearing capacity of this is 97.5%, and the maximum bending moment is 1.236 times the load in ULS. And by attracting yield lines, the bearing capacity is 102, and this is the maximum bending moment. So what does this mean? This means that when you are using attracting yield lines, in this case, it gives you more capacity. Because if you have 101, it gives you more capacity. If you comparing it with the yield lines without, of comparing it with the 30, 45, 60 rule. So it's all right to use this yield pattern, but be careful because you can have a yield situation or a yield line situation which is more severe.